Log on, tune in, find out. Another good idea from Cambridge.
Geodesic ray transform.
Geodesic ray transform, volumes,
And boundary distances.
and boundary distances in Finn's lab, including Romanian geometries.
Yeah. Okay, so let me start with the Romanian case, which more people are familiar with. So I will be mainly talking about Romanian metric on a disk. And I'm going to treat this space mainly as a metric space, which means that given a Riemannian structure, here I can define the distance between any 2 points. First, you define the length of a curve. The length with respect to g of gamma is the integral of square root of g gamma dot, and the distance Tj of xy is the length of the shortest curve between them, which is the infimum of this is and the general question is, suppose we know this function restricted on the boundary. Let me denote it by Pd g and call boundary distance function. It's just Pg restricted to the boundary. What can we say about the metric? What can we say includes, can we determine it? Can we find some invariance or whatever? And I will concentrate on the case when the metric is simple. And simple means that G is simple if first the boundary should be convex, strictly convex, which means that you don't have that your curves realized in distances do not bend over the boundary, and moreover there is a quadratic estimate how well. Formally, the second fundamental form of the boundary is positive definite everywhere. And second requirement for the simple metric is that geodesics have no conjugate points. And this means this is equivalent to saying that every 2 points are connected by a unique geodesic. For every xy from D, there exists unique geodesic, which I denote by as a segment in the plane. And this geodesic depends smoothly on x and y. This is equivalent to saying that all geodesics have no geodesic has conjugate point. And I'd like to note that this is an open condition, so the set of simple metrics is open in C infinity. And second, that you can detect simplicity by looking at the boundary distance function. So suppose you have a domain with something unknown inside, and you can only make boundary measurements, so put some wave and measure, say seismic wave, and measure how long does it take to go from x to y, and this is for all x and y. This means that you know the boundary distance function, and looking at this boundary distance function, one can detect if the metric inside is simple or not, because convexity of the boundary is easy, and having no conjugate points means that the boundary distance function is smooth, because well, it's easy to see one way, but it's equivalent. Given that the boundary is convex, smoothness of the boundary resistance function away from the diagonal is equivalent to having no conjugate points. So the major question is, what assumes that the metric is simple, because if it's not simple, it's clearly, this boundary distance function is clearly it's not a sufficient information to say many things, because what is the boundary distance? It's the length of the minimalizing curve. In the simple case, it's the length of that unique geodesic that connects that 2 points. And if the metric is not simple, then it can happen that there are regions where minimizing geodesic just doesn't enter. Any geodesic that enters here could be non-minimizing, so you just cannot see anything. It's sort of black hole. The metric's not simple. Well, you can relax this condition of simplicity, but let me restrict to the simple case for now. There is a conjecture due to Michel, and he proposed it in around 1980, in early 80s, I don't remember the precise date, maybe 81, which asserts that this function, boundary distance function, uniquely determines the metric if it's simple. So if G is simple and some other metric G prime satisfies, gives you the same boundary distance function, then the two metrics are isometric. And this is a hard question, and it's proved in a number of cases. I mean, for some classes of G's. So if, for example, what is known about it, if G is Euclidean metric, this is due to Gromov, 83 something, or G is, the dimension is 2, this is due to Pestov and Ullmann, and the publication date is 2005 or something like this. Then there is in higher dimension, it is proved if G is symmetric and negatively curved. And symmetric means that it's an isometric to a region in hyperbolic space or one of other four examples. Symmetric means homogeneous and negative, and so on. Symmetric, negatively curved. For example, hyperbolic. This is due to Besson, Courtois, and Gallo. It's 1995. And another partial case where rigidity is proved. Well, I mean that G is, say, hyperbolic, but G prime is arbitrary. Yeah, you don't. Another case is that G is C2 close.
So negative means not strictly negative.
Strictly negative. Strictly negative.
Strictly.
Yeah, the Euclidean case is here, and some intermediate cases. Well, product metrics are okay too. J is a product metric. This is due to Krook and Kleiner. And the date is like 98 maybe. I'm not sure exactly. So you can well, it's simple end product, which means that it's isometric to R, locally isometric to R and to something, product of this type. So you can split off, if you can split off a line, then it's okay. So this example are sort of symmetric. They're highly homogeneous, have large isometric groups. Then there is only, well, not only, but some open condition which guarantees that this boundary rigidity works, is that if G is C2 close to the Euclidean. This is due to Dima Buraga and myself. And this is, well, and similarly, well, essentially the same method proves that if it's C0 close to hyperbolic metric, then it's boundary rigidity. And I think this all the cases when boundary rigidity is, I mean global boundary rigidity, as I stated here, is proved. But I'm not going to talk about boundary rigidity. I'm going to talk about volume comparison, actually. And this is a motivation. And volume comparison, in some cases, in some situations, can be used to prove rigidity. For example, this one, and this one, these results of boundary rigidity are proved through volume comparison that I'm going to talk about. And here the proof is different, and here, well, some mixed. So what do I mean by proving rigidity by volume comparison? I mean the following conjecture which I want to advertise. Well, there's some introductory words about this problem. Okay, determining the metric is hard, but there are things that are very easy to recover if you know this boundary distance function. First, what you can recover easily further scattering data. And the scattering data is information about if you start with a given point and start a geodesic in a given direction, then you know where it comes. That's what it means, and well, and how long it will be, because we know the boundary distance data. And this is detected by taking one derivative, because if you know the boundary distance, you can differentiate it with respect to one of the points. And by the first variation formula, what you get is this angle, cosine of this angle. So for every pair of points using the derivatives, you can find out the direction of this vector in the sense, well, you have only access to the boundary, so one needs to be more precise what it means to determine this vector. For example, you determine its orthogonal projection to the tangent place, and you know that it's, well, let me say that all geodesics are unit speed, parameterized by arc length and so on. So you can easily determine the scattering data, and once you have done this, you can find out the volume. This is theorem due to Santalon, very classic thing, about 1960, which says that boundary distance function for a simple metric, which is simple, then boundary distance function determines the total Riemannian volume. And this is done as follows. First, you know the scattering data. So for every point in every direction, you know the length of the geodesic that emanating. And using the fact that the Liouville measure is invariant on the geodesic flow, you just integrate the characteristic function of the unit tangent bundle, and it turns out that you have to integrate this length, multiply it by some cosine of some angle, like this angle with the normal, and integrate it over the boundary and over all vector, and this gives you the volume. So it's very easy, and this motivates this says that the following conjecture is sort of plausible. And this is a conjecture that I want to advertise. It says the following: if J is simple, and G prime is any metric such that it induced at least the same boundary distance, I mean this inequality is pointwise, then the volume of the disk with the metric G prime is at least as large as the remaining volume of the disk with the metric G.
So
Well,
you assume that G prime is
well, in the conjecture, no.
Is it point-wise?
Yes, at pointwise, yes. So this means that if you take any pair of boundary points and measure the length of minimizing geodesic with respect to two metrics, the G prime will give you longer. This is very natural to assume given this fact, especially if you restrict to the case when G prime is simple, because, well, you have a formula that given the boundary distance, it gives you a volume. It should be obvious if distances are larger, then the volume should be larger. This formula should be monotone. Well, it's not that easy as it sounds, because the formula, if you write it down, it depends on derivatives, two derivatives actually. And if you start plugging arbitrary function in place of this boundary distance function, then the result of this formula, that would be not correct. So if you generalize the conjecture saying that take any two functions such that one is larger than the other, plug them into this formula for volume in terms of boundary distance functions, then you assume that the result of the formula for the larger function will be larger. That's not true. And the problem is that not every function is a boundary distance function. It's actually a very hard problem to determine, given a function, if it's a boundary distance or not. Well, of course, it should satisfy triangle inequality and some other trivial things, but beyond that, there are some conditions. And
In that conjecture, are you assuming that G prime is simple as well?
well, in conjecture, no. Well, and in conjecture, actually, let me say about, well, if you prove it for simple metrics, that's good too. It's open for simple metrics too. Well, why non-simple metrics don't make it less natural? Because the metric being non-simple means some black holes, essentially. And you can push black hole out, shrink the metric in the black hole until it becomes having no conjugate. Well, it's not possible, but I'm talking about some naive considerations. So being non-simple just makes the volume larger. Let me. Well, anyway, for simple metric, it's a very sensible thing to ask as well. And how it relates to the boundary distance problem, boundary rigidity problem, which is to determine the metric, is in some cases this conjecture is proved, and some proofs allows one to analyze the equality case here. And during this analysis, one can prove an isometry. And this cases where I had a star on the boundary rigidity, these theorems are proved this way. And there are, so let me list the list of cases when this conjecture is proved. I mean, the list of metrics G for which the conjecture is proved, known for yes, the Euclidean metric is fine. This is due to Bezikovich.
And that's what argument, right?
Yeah, so
This is full conjecture.
yeah, full
G
conjecture.
prime.
G prime is arbitrary, and this is very old. And the only reason what Gromov did with boundary rigidity for a simple metric, he just noticed this passive proof. Because this is essentially Bezikovich, classic Bezikovich inequality. Don't want to spend my time writing down the inequality, which is about the volume of a Riemannian metric on a cube. But anyway, it's very simple and classic. The second case where it's known, it's dimension 2, and I proved this in 2092, approximately. But the method of proof doesn't allow to analyze the equality case, so boundary rigidity was eventually proved by analytic methods. And this proof didn't work. And as I already mentioned, if G is negative, rank 1 symmetric, okay, negatively curved symmetric, this is what Besson, Courtois, Gallo did in the famous 95 papers. Actually, they did much more. They proved some volume inequality for some volume entropy inequality, but this conjecture is a partial case.
How do you go from the result in the closed case to the boundary case for this conjecture? Because when you
well, you just include well, to your metric G, say it's hyperbolic, right?
I guess maybe I'll make a more precise question. When you have the same boundary distance function, you have the same jet, and then you can glue and make a conjugacy of the geodesic flows.
Yeah.
If you have just inequality, how do you relate the geodesic flow?
You don't have to relate geodesic flow. You just what they did. They constructed a map from one metric to the other, which is area non-increasing. They didn't do anything with geodesic flows. They just did it with metrics. And they have proved the inequality. Volume entropy is the rate of growth of the volume of balls in the universal cover. And what they did, they sort of mapped universal cover of one space like this, of any metric on a closed on a universal cover to the symmetric metric, say for example hyperbolic. And they did it that way, in such a way that this map was area non-increasing.
Right, but what is the volume growth there? You just have a disk with your...
I have a disk, but they had a universal cover of piece. And to derive this conjecture, you just glue your disk somewhere inside.
That's right, but for the gluing you need to have the same infinity jet.
No. It's all okay for piecewise continuous metrics.
Is it?
Yeah. Though this result, it's fine. It's very robust. You can. Well, actually, there is another result which says that if the boundary distances are the same, then the infinity jet is the same.
That's exactly what I was referring, but here you have just an inequality.
Well, I mean the following. You have a proof of inequality. You look at this proof, inside the proof. And inside the proof you have a map which is doesn't depend on derivatives at all. It depends on some very robust characteristics. And at the end this map is area non-increasing. And you can analyze the equality case and see that its area preserving if and only if it's an isometry. So you take another metric. So suppose you are proving boundary rigidity, right? First you observe that two metrics have the same volume. And in this case, actually in this case, the C infinity jet is the same. So you don't have to worry about this problem. But the proof works for piecewise continuous, something like this. G prime can be well, I don't know what is a reasonable functional space, but piecewise continuous is definitely okay. The next is G is almost Euclidean in C2 sense, or G is almost hyperbolic in C3 sense. This is the result that I mentioned by Dima Buraga and myself. This is also fine for piecewise continuous metrics, and anyway, if you want to prove boundary rigidity, then you know that C-infinity jets are the same, so it's not a problem to derive. The problem is that your proof of this inequality must be robust and must be not robust, must allow to analyze the equality case. So somehow, if it involves, say, some kind of area non-increasing map, then you can try to analyze when this map is area preserving and hope that it's going to be in isometry. But if it's another proof, you couldn't some approximation proof, then it may not work. So sometimes this proving this conjecture implies boundary rigidity, sometimes not. So what I want to talk about today is a local version of this conjecture. So the theorem I want to prove, well, I don't know if I have time for proof, but at least formulate that if G is close to G prime, and well, unfortunately, let me say in C infinity. The proof I have needs some like 3 or 4 derivatives. I didn't count because I'm a geometer. I don't know how to count derivatives. Well, anyway, then, and G prime induce the same or greater boundary distance function pointwise, then the volume of the disk is G prime is greater or equal to that of G. So this is the local version, and approximately equal means that they both should belong to some neighborhood of a diagonal in the space of simple Riemannian metrics. Or like for any metric G naught, there is a neighborhood of G naught such that if both belong to this neighborhood, well, I'm not writing this down because.
So this implies that G prime is also simple, right?
Yeah, because it's an open condition. It's of course once you say this, you are inside the class of simple metrics. So everything is simple, and in principle, it should be. It might be possible to prove it by analyzing the formula, but I couldn't do this because, well, there are some conditions. Not all functions are boundary distance functions. If you plug in arbitrary function, it's easy to construct a counterexample. So some function which pretends to be boundary distance, you plug it into the formula, and you can perturb it a little, so that the function is increased, but the output of the formula goes down. So you need to use somehow that it's not an arbitrary function, but all this triangle inequality and more complicated stuff. Like, well, I unfortunately I don't know, and nobody knows what are the conditions that you should assume about the functions for it to be a boundary distance. It's very complicated. And before I go further, let me mention that this theorem easily implies well-known thing, namely the injectivity of geodesic ray transform. So let me say a little bit what it is. So we have a simple metric G, and let me denote by gamma G the set of all geodesics. I mean maximal geodesics, going from boundary to boundary. This is a manifold, smooth manifold, which is diffeomorphic to boundary times boundary minus the diagonal, because each geodesic is determined by its endpoint, so it's manifold. And suppose we're given a function, suppose we have a function inside, and we know its integrals over all these geodesics. It's a function on gamma G. And the result, the corollary, and it's well known for a long time, that this this geodesic ray transform is injective. So we have ray transform I j from C infinity of d to C infinity of gamma g, which is the following: ej of function f. So suppose f is here, from here, applied to a geodesic is just the integral of the function of a geodesic. And the corollary is that ej is injective. This means that if you know integrals of a function of all geodesics, then we know the function. This is what it means. And this is not new, and this, in Romanian case, it was proved independently by Muhametov in, well, it's hard to tell the date because there were several publications. Let me put about 1980, and independently by Bernstein and Gerber, approximately the same time. But this volume comparison result, their proof was, both proofs were very analytic, long and analytic, full of formulas. Yeah. Let me show you how that volume comparison thing implies this injectivity. Well, actually, this injectivity is essentially this volume comparison thing applied to metrics conformal to each other. So suppose we have a function f on the disk, smooth function. I don't know how many derivatives you need. It's not my area of expertise. And all the integrals. The integrals of all geodesics are 0. Now let me choose this very small epsilon and consider a conformal metric, g prime, which is 1 of plus epsilon f square to g. And square because g is a quadratic form. So for length you have just 1 plus epsilon f. And what do you see about, consider some geodesic of the original metric, gamma j.
It can be 0.
Epsilon is small.
No, I mean if f is negative.
Okay, this is 1 plus, it's smooth, it's smooth. It's a smooth function, don't worry about it. Consider the geodesic of the original metric, gamma. And let's try to find its length with respect to new metric. What you get is the original length by just integrate this square root of this over this line, plus this ij of f, which is 0. So all the geodesics of the original metric have.
By epsilon, right?
Okay, yeah, right. The geodesics, all geodesics have the same length. But these all geodesics are not geodesics of the new metric. Geodesic of a new metric is something, well, possibly something different, but it's shorter because geodesics are minimizing curves. So what we conclude that boundary is, so let be x and y, boundary distance of g prime between x and y is smaller than boundary distance of g between x and y. And this, by theorem, this implies that the volume of g prime is smaller than the volume of g. And what is the volume of g prime? It's the integral of this thing to the power n. So it's smaller than the integral of 1. And now you just repeat the argument for f for minus f in place of f and add together, and that's it. You conclude that the integral of 1 plus epsilon f to n powers plus to minus epsilon f to power n is greater than integral of 2. And this is smaller than like integral 1 plus epsilon square f square for trivial reasons. Just expand the Newton binomial. And that's it. So you have that the integral of f square is negative and non-positive. And therefore, yeah, sure. Sure. And this is just Taylor, not Taylor expansion, but Newton binomial. So this is how this thing follows. And now let me tell you about the Finslerian case. Well, the proof, how the proof goes of this theorem. The main idea is to generalize the theorem and prove it for Finsler metrics. I will tell you about what is a Finsler metric is in a few moments, but actually the Riemannian proof relies on the Finsler geometry. You need an intermediate Finslerian construction. So theorem 2 is that theorem 1 is true for Finsler metrics. I will not write it down again.
What is the volume then? I mean, you take your opinions of whether you can.
Yeah, I have to specify what is the volume, actually, but well, I will tell about it. Okay, so this is a preliminary formulation, and you immediately get the same corollary for Finsler metric in the geodesic ray transform for a simple Finsler metric. Is injective. And this is not new either. It's Sharafudinov proved again by a very long analytic paper. Sharafudinov in 1996. So it's known, but this way of proof gives a short and reasonable proof. Actually, this theorem is not very hard to prove either. The proof is really simple compared to.
His proof is also simple. Can I just say that? I mean, he just proves an L2 identity. His best 2 identity.
Yeah, I know. He goes for for Finsler metrics.
Yes.
Well, he actually proves some more because he also
proves a best 2 identity for Finsler metrics.
Well, okay. It depends on one's view of what is simple. Since I'm a geometer, it's for me geometric proof is much simple.
Okay, but
it's just a new
I'm
proof. So let's look at this.
It's not that complicated. I mean, it might look a little complicated because it uses tensors and so on.
Okay.
From a conceptual point of view, it's very natural.
Maybe you're
Energy
right.
identity, like.
Yes, I know he goes through passive identity. Okay, it's just another proof. Okay. Just geometric proof. Okay. Well, actually, I was interested in this result. I just recently tried to think about this and try to study about who did what and so on. Let me explain why Finsler metric helps. Why going to Finsler argument helps here. Helping this to prove theorem 1. So that's the main thing. The proof goes in. I need to tell you briefly what is Finsler metric and what is volume. So you need to choose carefully what's the definition of volume for Finsler metric. So Finsler metric to say briefly, it's a homogeneous Lagrangian system, but geometrically you can define it as a function from the tangent on the manifold M, from the tangent bundle to the negative reals, such that for every, which is smooth, away from the zero section, so that for every x on the manifold you have the restriction of phi to this tangent bundle is positively homogeneous which means that phi of lambda v equals lambda phi of v for the negative lambdas. I don't assume any symmetry, so
That's the length, right?
yeah, phi is a length. It's square root of g, essentially. If Riemannian metrics are partial case, if you define phi as a square root in second, it should be strictly convex. Convex function. And I prefer to think about it as a norm. So if you have a manifold x, a manifold M, point x, in the tangent space you have a norm, which may be non-symmetric, but I still call it a norm, which defines the length of tangent vector. So this picture draws, on this picture I draw a unit ball of the restriction. It's a strictly convex body in the tangent space, and its boundary is a set of vectors that we assign the length 1. Then we define the length of a curve, the distance, which is not symmetric, but anyway, it's a sort of distance, and go through all this. What is the volume? The volume, there are several definitions, actually many definitions of volume for finite metrics. And what I want to use is so-called Holmes-Thompson volume. Which is the following thing. First of all, you consider the dual norm on the cotangent bundle. Phi star is a dual norm. Which is a map from cotangent bundle to the negative reals, which is pointwise dual norm. So you just can define it's a supremum of h of v, where v is from tangent space, and have unit norm. In this, you apply this formula pointwise. No, absolutely. No. Well, h is h is from the cotangent bundle from some. It's a covector at some point, and v is a vector from the same tangent space.
So then,
Yeah, I don't put absolute value here because my metric not symmetric. Yes, they are not symmetric. And the unit balls are polar to each other. So it's if you apply this construction again, you will return to the original metric. So this is just standard duality, and this is a norm. Well, in the same sense, it's not symmetric, and you can consider its unit balls. So let me define B star of phi is a set of all covectors of norm at most 1. This is a bundle of unit balls. And it belongs to, it's contained in the cotangent bundle. And in the cotangent bundle we have a canonical symplectic volume, which doesn't depend on coordinates because, well, it's standard thing. And I just define the volume of Finson manifold, which is Holmes-Thompson volume as some constant depending on the dimension only times canonical volume of this set. Why it's a good definition? Well, first of all, it's monotonous with respect to metric. If phi prime greater than phi point y, then the volume of phi prime is greater than the volume of phi. So it's geometric. This is because the inclusion, when you enlarge the norm, the dual norm shrinks, and so the balls grow up. So just in this case, you just have b phi prime contains b phi star. So it's natural from geometric point of view. And the next thing is that it's good from dynamics point of view, because this canonical volume is a measure preserved by the geodesic flow, by Legendre transformers, by the corresponding Hamiltonian flow. So this volume corresponds to the invariant measure on the unit tangent bundle, invariant under geodesic flow. And you can apply that integral geometry that leads to Santala formula for the volume. So basically, the first step in the proof is to extend Santala formula to the Finson geometry. Step one is that Santala formula for volume works for Finson metrics. So if you plug a boundary distance of the simple Finson metric into the same formula, you get this Holmes-Thompson volume. For precise same reason, because you integrate something over geodesics, and using invariance of the measure under the geodesic flow, you reduce this to integration over the boundary, and the formula is the same. Well, that's something. And step two, well, I will simplify things. What I will say now doesn't actually work. It works to prove a Vickers statement where perturbation of the metric is supported strictly inside the ball. But it illustrates the idea. The actual technical data is a little bit more complicated, but what I will say now works for the case when the perturbation of the metric is separated away from the boundary. So the two metrics coincide near the boundary. Step two is the following. So suppose phi and phi prime are Finson metrics, simple Finson metrics. And the boundary distance of phi prime is greater than or equal to that of phi. And they are close to each other in a suitable sense. Then there exists new Finson-metric twiddle, which induces the same boundary distance function as phi prime. And its majorized as 5.5. So what happens? You have the same disk. With two metrics in it, phi and phi prime. This, what is the easiest way to compare volume? To compare it pointwise. So if phi prime were larger than 5 pointwise, then that would be trivial. But of course it's not. The most you can have any examples like just apply any diffeomorphism, coordinate change, and so on. But what you can do is that The point here is that Finsler metrics are flexible. You can perturb a Finsler metric in many, many ways so that the boundary distance remains the same. And actually, you can perturb Finsler metric so that to induce a given perturbation of the boundary distance function. This is absolutely impossible in the Riemannian case. So to make this proof work, you need to go through Finsler metrics. So you can start with Riemannian metrics here, but the intermediate metric will be Finslerian anyway. So that's why the proof I have works only through the Finsler geometry. Maybe you can translate it into Riemannian terms somehow, but then it will be a very, very, very complicated thing. And so, well, once we have this, the theorem too follows, because this in Santalo formula implies that volume of phi twiddle is the same as the volume of phi prime. And this, for trivial reasons, implies that the volume of phi twiddle, this is due to Santalo formula.
That's, I think, it's more than 5.
More than 5, yes. No.
Two is 5.
Oh, yeah. So the goal is to perturb this metric phi prime, and using the fact that it's induced large boundary distance, make it larger than prescribed metric phi. And this can be, let me explain. This is an idea, actually. This works in a straightforward way only if the perturbation is supported in some small region. And if it's not, it almost works, but actually you need to extend the metric and consider distances between the extended metric and something like this. But the main idea is covered by this case. And
So you play like a coordinate of the pressure.
Yes, but then when you glue in another metric, you have non-smooth discontinuity here, and so you cannot just repeat the argument for the extended metric. You need to modify it somehow. So what you have is just a family of certain functions which are not exactly well, I don't want to speak about the general case. Just don't have time. So how the thing works in the special simplest case when the perturbation is strictly inside. First, I want a way to define Finsler metrics. And the observation here is that the distance function to the boundary determines the metric, if the metric is simple. It's a very easy observation. Let me consider my space, Finsler space, or Riemannian, it doesn't really matter at this point. And for each point P on the boundary, I consider the function Fp on the disk, which is just distance function from P to S. So its level sets look like something like this. And if the metric is simple, then the family of these functions, if you know all these functions, determines the metric. And in some explicit way. Let me consider fix some point x inside and consider differentiate every function from my family. And well, it's easy to see that the derivatives of the function have unit norms because they are distance functions. So phi prime of this dx p phi star equal to 0. And the next thing is that the gradients of these functions of p are just velocity vectors of the unique geodesics, and they parameterize the unit sphere.
And you can do the case the same.
Yeah, the Finsler case is the same. So the derivatives, which are general transform of the gradients, parameterize the cotangent sphere. So this set parameterize the unit sphere of the dual norm at this point. So if you know all this, you know the dual norm, and by duality you know the Finsler metric. And the good observation about that if you perturb this family of function, this is the first observation. And the second observation is that if you have another family of functions, f prime twiddle, which is close to our original family, well, in C infinity, actually you need 3 derivatives.
When approach point P,
Well, actually it's a function in 2 arguments. The first argument is on the boundary, this is P,
yes?
and the second argument is in the disk. So actually this family of function is a function on the Fp. You can associate it to a function from the boundary across disk to R. It's not smooth at the boundary.
Yeah, right.
So this is why I need
Right, yes.
this is why I need to get into, but well, some technical things, some slightly different construction and so on allows you to do. So assume that we perturb this family of function in
Outside zero.
outside the boundary, yes. So each function is perturbed in some smaller region, and all family is close to the original family with all derivatives, including the derivative with respect to p. So as a function to argument. And then, so assuming all this, then there exists a metric phi prime, for which this new family is a family of distance-like functions with unit gradient, for which, well, actually, in my special case, they will be just distance functions to points, for which fp prime is the family of distance functions.
Oh, well, that's something interesting.
Yeah, how to do this? So we perturbed our family of functions. So this induced a small perturbation of the family of derivatives. So originally the derivatives parameterized some strictly convex, the surface of a strictly convex surface in each tangent space. When we slightly perturb it, assume that 3 derivatives are close to the original one, this is the family of derivatives of the original functions. This this surface, this map from the boundary to the cotangent fiber, will be perturbed by C2 small correction sum. And strict convexity is a condition on third derivatives. Something in terms of first and second derivative is positive. So the perturbed thing will be again a strictly convex surface in the tangent bundle, and you can lose symmetry at this point, because even you restrict yourself to symmetric metrics originally, at this point you lose it. This is again strictly.
Actually, if you put some extra condition on left,
Yeah, they are hard to satisfy. This extra, yes, you can put extra condition, but they are very hard to satisfy. I cannot Actually, I cannot do this in general. It's an interesting question. Can you realize any symmetric perturbation of the distance function by a symmetric perturbation of matrix inside? You can do it in smaller region for almost flat things, but in general, I don't know if you can do that or not. And this is a very simple thing. So they give you a strictly convex surface. So this new strictly convex surface form is a unit sphere of some strictly convex norm. So you get this phi prime twiddle. So this defines the norm phi star twiddle at the point x, and this by duality defines the norm at x. So we define thin symmetric. What remains to observe is that this is a new our perturbed function are indeed distance functions. But that was by the construction, because the gradients has unit length. Any function with unit length gradient is a distance function. A distance function from something. But because the perturbation is identical on the boundary, this level sets are the same, so the distances are the same. And actually, it doesn't matter. In fact, it doesn't matter if it's a distance function of points or not. If you have any family of distance-like functions, you can compute the volume by Santalo-like formulas. Actually, this is what I have to do to cover the case of not for any the general case, not just the perturbation strictly inside. You slightly generalize the Santalo formula. But anyway, that's technical details. So it remains to apply this construction to achieve, I don't have time, but let me just write down the formula. It's straightforward to verify that it satisfies all the conditions. So we have two metrics phi and phi prime inside our region. And for each p, we fix p on the boundary. And I want to define some function which serves as a distance function from p for the new metric, which has to be, which is going to have the same boundary distances as phi, as for prime, and point-wise greater than this one. So what we do is, so fix x inside, and consider the phi geodesic from pi through x up to the boundary. This is phi geodesic, and we define pi twiddle of x by some explicit formula. It's just the distance phi from p to x times distance phi prime from p, let it be q, pq divided by p phi prime pq. And this satisfies all things. So essentially, you make your function, you define a new function along each geodesic separately, emanating from phi, and it's just proportional to the original distance function, but the coefficient depends on the geodesic, and it's chosen so that the value at the endpoint is the same. That's the formula. Well, and it's sort of straightforward to verify everything. Because, well, it's small perturbation, so it's a distance function of some thin symmetric, and this thin symmetric, well, so because the derivative of fp along this geodesic.
Because we assume that the phi and phi prime are close, right?
Yeah, sure. They are close, so well, as a perturbation is supported inside, so you don't care about problematic derivatives here. So this works for the model case when the perturbation, and the general cases, the formula is slightly longer. Well, and the formula is not longer, but well, you need. You need to be careful when you associate a geodesic with a point. Actually, the problem is when you extend the thing and plug in and glue in another metric with discontinuity. You need to be very careful what is the relation between old points, and because you no longer get distance functions from points and such things. But otherwise, so I think it's a good point to stop at this.
Yeah, thank you very much. Other questions?
I just have one
Mhm.
question. Maybe you must have probably thought about this. Is there any chance you could use your theorem for getting injectivity results rather than for functions from higher order tensors?
You mean tensors?
Like a one form.
Well, for one forms it's known, right?
Yeah, it is now.
Well, maybe yes, because those old works of Mukamedov and Bernstein, they actually did it for one forms. They're using some similar things for Riemannian metrics. Essentially, they derived it from boundary rigidity for conformal classes.
Yeah, okay, so let me rephrase the question. Can you get it for two tensors?
No,
Okay.
no. Well, maybe something. The problem with two tensors is that they're too bound to Riemannian case. Two tensors are very Riemannian. The injectivity of the Ragland's form. Well, there may be other methods.
Yes.
Yes. So actually I can think in dimension 2. I'm fairly sure that someone can just analyze the formula, and because the conditions. Because the result is true for fields and metrics, the conditions, what functions are boundary, this function should be simple, reasonable. I think it's doable through straightforward analysis. I don't claim it's something great, it's impossible to prove in any other way, but it's nice, and you see the proof is short, it's geometric.
Other questions? Thank you very much.